Okay, welcome everyone. So today we're going to look at these single qubit gates that I talked about in a lot more mathematical detail and a lot more physical detail as well. We have the X polygate, the Y polygate, the Z polygate, the Hadamard gate, and we have some phase gates that we're going to look at as well. Now, what we've done is kind of the orthodox teaching wisdom in reverse order. Usually, when you're learning, let's say, arithmetic or algebra, what happens is you learn in, let's say, arithmetic, you learn all the operations and all the simple stuff first. You learn addition, subtraction, division, multiplication, and the primitives like the numbers first. And then you learn all the interesting stuff you can do with those things, right? Like accounting and all the applications and things like that, right? Ledgering, finances, all that kind of stuff that you can do with addition. The world's your oyster once you know how to add numbers together. When I think philosophically, I really hold that it should be done in the reverse order. I really think there should be at least some wetting of the whistle when it comes to the applications. I feel really strongly that you should be shown or at least motivated to learn the primitives by what you can do with them. That's why I've shown you super dense coding first. That's why I showed you quantum teleportation, even though you didn't totally understand what these polygates were yet. You didn't totally understand what the Hadamard gate was yet. I tried to show you on a somewhat, I don't want to say superficial level, but on a less exhaustively, not exhaustively rigorous level, um, what these gates were and what you could do with them without fully going into the exhaustive mathematical details of what these gates actually are and how they operate and how they fit into the larger context of Hilbert spaces and physics and quantum mechanics and all these kinds of things. Now I want to kind of fill in the gaps and do that with you now that you're kind of motivated to learn these details. So let's start with the polygates. These guys are really, really important mathematically in general and also in the context of quantum computing, quantum mechanics, all these kinds of things. So the quantum not gate, aka the poly X gate, let's start there. It seems like a really natural place to start. Um, let's see here. Find my Figma. Right. And you'll see here I kind of have if you recall, this guy here is called the block sphere. No, that. Thank you. The block sphere, right? Sorry, I'm kind of getting used to this thing. Block sphere. And the block sphere is a neat mathematical representation of a single qubit. Recall that a qubit is the quantum version of a classical bit, the things in a classical computer that can be either a 1 or a 0 and are the basic unit of state, the basic unit of what everything is in a computer at any given time. Anything on your screen, anything anywhere on your computer is represented as the sequence of what all the bits are in, whether they're ones or zeros, and the combination of all these things. So it is in a quantum computer. Everything in a quantum computer at any given time is a function of what these qubits are, what state they're in. But it's a little more complicated in quantum mechanics, remember. We don't know really what state anything is in, and it doesn't even have a state. So that's what we think about when we think about these qubits. Classical bits are easy to think about conceptually. They're either 1 or they're 0. It's very, very difficult to think about a qubit. That's why we have these nice little diagram here. It still looks a little complicated, but it's a lot easier to kind of think in our mind. It's like it's a 1 and it's not a 1 and it's a 0 at the same time, and it's a wave, but it's a probability wave, but it's not really a wave, it's a particle. This block sphere is a lot nicer mathematically to think about or visually to think about. It's a lot easier to kind of see the qubit and think about more importantly the transformations we're going to do on the qubit when we're doing these kinds of gates on it and stuff like that. And these gates are going to be the building blocks of quantum circuits, and quantum circuits are the model of quantum computing. So when we talk about quantum algorithms and we talk about quantum communication protocols like we did last time, any type of quantum computing or quantum information that we talk about in the field, we pretty much always talk about it in terms of these quantum circuits. So it's really important that you think about these gates and get a good intuition for how they act and how they change qubit state. That's why it's really important we think about these block spheres and have them as a tool here. So let's first talk about the X gate as promised, right? What does the X gate do to these guys? Well, it just kind of flips a bit, right? It flips it from a 0 to a 1. And in fact, I'm gonna bring another tool to bear here. Um, we were talking about quantum computing, and there's actually a language of quantum computing. There are a couple of others, but Quizkit is my favorite. So what I'm actually going to do for you here um, is go through. Let's see here. Yeah, I'm actually gonna in Quizkit. I'm actually gonna go through. Eventually, we're gonna do full quantum algorithms in this language, but for now, I'm just gonna put some quantum state down, some quantum state vectors, and I'm going to put them through these quantum gates, and I'm going to show you how they actually transform on the block sphere here. And in doing so, I'm going to kind of give you an introduction to Qiskit as a software, and I'm going to kind of show you how we actually write these things, because I don't want you to just think of quantum computing as some like pie in the sky dream. It's a real thing. Qiskit is a language created by IBM. This particular implementation I'm using now is being simulated on a classical computer, but you can actually interact with IBM's backends, and they have real quantum processors that you can actually run these things on. So before we do that, let me just actually write down what the matrices are mathematically first. So the X polygate is the flip matrix. I think we've seen it before. I think it was actually in the first notes as the classical NOT gate as well. No, actually it is. Yeah, so it gets a 0 there. Okay, that's the poly X gate. It rotates about the x-axis by 180 degrees. It flips about the x-axis by 180 degrees. That's the x-axis, I believe, in this diagram. So if you are a 0-bit, you will be flipped to a 1-bit. And similarly, this is why we're using this visual representation, because it's easy to just remember this. But if you're not in the 0 state, then you need the block sphere for this kind of geometrical representation. That's why you need, for example, and remember the state of your qubit has to sit out here. It's not allowed to be in here. That's not allowed. It has to be on the outside of the unit sphere. So wherever it is, when you act on it with this X polygate, it's just going to rotate by 180 degrees about the x-axis, right? That's what that one does. Okay, how about the Y? The Y, I'm going to need to look at my notes just to make sure I don't get it wrong, because it'd be a great historical injustice given the significance of these matrices. I0. Notice something important about the X poly matrix. It is its own inverse, right? You apply it twice, flips it right back. 180 times 2 is 360. So 2 of these applied is its own inverse. Similarly for the Y. This is the same, but about the Y-axis. Now the Z. This is the same for the Z-axis. Okay, so yeah, these are the three poly matrices. And then of course we had the Hadamard gate, which we discussed in detail. We used this a lot. If you recall the Hadamard gate, the two operations we like to do most with it were put a 0 through a Hadamard gate. And make sure these are showing up on the capture. Yes, very good. Okay. And it would result in this. And on a 1, it would do the same thing, but with a minus here. So the Hadamard gate is kind of called the square root of this guy, because this guy flips, and the Hadamard gate in turn actually kind of puts it halfway in between, right? So what the Hadamard gate actually looks like, so x plus a z. The z, because it picks up a phase as well, over square root of 2, because it's not a full flip. That actually takes this form. Right? So that's what those guys look like. Now, there's something about important about the Pauli matrix. Well, there's like a million important things about the Pauli matrices, but there's something important that's also extremely relevant right now to this diagram that I've just drawn here. And there's an easy answer to why they correspond to these rotations about this block matrix here. The Pauli matrices are actually the infinitesimal generators of the SU2 space, which are the rotations over two-dimensional, all two-dimensional unitary operators, rotations over this 2 by 2 space. In general, an infinitesimal rotator is corresponds to an infinitesimal rotation over two-dimensional space here, right? Um, so what we have here is, or three-dimensional space, or sorry, rather. Um, so what we have here is um these these whoops. These Pauli matrices are Hamiltonian operators. That means they correspond to observables. And in general, they're going to be corresponding to spin in quantum mechanics. Um, but if you exponentiate a Hamiltonian um, operator, you always get a unitary operator, or this is always unitary. It's always a unitary operator. And if we call unitary operators are operators that can change a quantum mechanical state legally in quantum mechanics. If if they're the only operators that can do anything to a quantum mechanical state and actually change a state moving forwards in time. By quantum mechanics, you'll violate quantum mechanics law if you operate on a quantum mechanical system in a way that is not unitary. In fact, it leads to very strange paradoxes. It will violate locality. It will allow you to go backwards in time. It will allow you to transmit information faster than the speed of light. You'll be able to do all kinds of weird things, right? So it has to be unitary. Um, so these, in particular, these Pauli matrices, the reason that they correspond to rotations on the block matrices is because they're the infinitesimal generators of a particular unitary operation, which is this rotation about this block sphere and this space here, right? On this, on the face of this unit sphere, SU2. SU2 corresponds to a rotation along this unit sphere. Um, so what do I mean by infinitesimal generator? That's kind of a good question, right? That sounds a little bit like a buzzword. What I actually mean by that is that they represent an infinitesimal itty bitty rotation, right? Specifically like this tiny, tiny, tiny little delta, right? Lowercase delta. So if you have this little tiny rotation, right? Each of these matrices, this is a tiny little rotation around the X, this is a tiny little rotation around the Y, this is a tiny little rotation around the Z. So if you compound them and you want to have longer rotations, you get an exponential function out of that, right? Because if you have many, many, many of them and they keep getting smaller and smaller, smaller, in the limit, eventually you're going to have an exponential function because that's the definition of the exponential function, one of many. N to the power of n and keep making n larger and larger. So this gets bigger and bigger. So this gets smaller and there's more and more iterations. Eventually you'll get this e to the power of that, right? That's the definition of the exponential function. So that's why, no, that could pretty much stay where it is. That's why when you exponentiate each one of these little infinitesimal operations here, you get a continuous rotation rather just an infinitesimal rotation, right? So that's the significance of the Pauli matrices and why they generate this thing on this block sphere here. Now let's go to Quizkit and actually see these things perform these operations so that you don't have to take my word for it. You can see that they actually do what I say they do. Where are we here? Right. Okay. Oh, I should need to do the imports. Should have really done that beforehand. Um, Wonderful. This is going to be difficult. All right, bear with me a moment here. Okay, got the imports. Where were we? All right, let's initialize a quantum system. All right, so we'll initialize a quantum circuit. Just call it QC. Quantum circuit, and we'll just give it 1 qubit for now. Um, and we want to convert it to a format which we can represent on the block sphere, just so we can kind of see what the thing looks like. We haven't done anything to the quantum circuit yet. The quantum circuit is just kind of like a blank thing. Uh, block. Right. So it kind of just looks like this for now. We've initialized it in a 0 state. All right. So we've been talking about the X gate. Let's put it through one of those first. So put the quantum circuit through an X gate. It only has 1 qubit, but we have to tell it to just put the first qubit through its 0 index. So the 0th qubit is the first one. Good. So we've put it through a quantum gate here. We put it through the X gate, the poly X gate. So it should flip to a 0 now. QC psi, we'll reassign psi to uh, this state vector. And again, the state vector just kind of puts it into the coordinates that are appropriate to the block vector. It's just a coordinate transformation. QC. Good. And hopefully we'll see it down at 1. Yes, good. Just a good old-fashioned quantum flip. All right. Uh, Now let's put it through the Y gate. Yeah, in fact, you know what? Let's leave it here. QC. Yeah, you know what? Let's flip it again, actually. QC dot X 0. And then we'll just turn it back into this wave vector again. Good. So you see that the X gate is its own inverse, the quantum flip. Let's put it through the Y gate now. Whoops. Quantum circuit. Put it through the Y gate. And you can imagine this as a quantum circuit steps. First iteration was the X, then another X, and now we're going to be putting it through a Y. And the 0 here is just telling me which qubit. It's only a 1 qubit state, so this is just a formality. And then we're just converting it to a state vector. Then we're just going to plot it again. And this is a block vector here, of course, that I'm plotting on. Okay. Oh, yeah. 100 degrees around the y-axis. Yeah, okay, I suppose that. Right, yeah. So these are both going to look exactly the same. That's not particularly interesting. Right, so it's going to rotate the same thing about the x-axis and the y-axis. They'll look exactly the same. That's not particularly interesting. Let's put it through a Hadamard gate. That's much more interesting. And yeah, a Z won't really do much here either. We should put it through a Hadamard gate first. All right, so I'm putting it through a Hadamard gate, right? And then size, just reassigning the variable psi to this quantum circuit, which has been through two X's, a Y, and now a Hadamard. Right, and now we're gonna see what happened. Hopefully it will be at the equator. That's what we're hoping. Because as a Hadamard is the square root of flip, as we know. It is at the equator. Very nice. Right. So this is a taste of Quizkit, and this is kind of what these operations do on a single qubit. And I want you to keep in mind the block representation as we're going through these kinds of things, and mathematically what the Pauli matrices kind of mean. Historical context, it's important. And Quizkit, we're going to be using that as a visual aid tool. And later, when we're doing actual quantum algorithms like QFT and things like this, we're going to be using it to actually take measurements after we've done the algorithm and things like this, and draw the circuits and things like that. So I hope you've enjoyed the a more mathematically detailed view of the single qubit gates. I'm going to kind of continue with that sort of thing before we do more complicated algorithms like the QFT. So next time we're going to do multiple qubit gates and look at control gates and things like that. Hope you've enjoyed. Cheers.